Hello guys. So today we are going to discuss the topic diode transistor logic. As the name suggests, diode and the transistor logic, the logic that would be created that would be with the help of the diode and the transistor. So as we did in our previous lectures, what we'll do, we'll get the basic concept clear first. That would be actually aiding you in your main explanation. So here we have got the two new words, that is the diode and the transistor for our logic setup. The transistor, we'll discuss it first, then the diode. Now, in the transistor, it can be used either as an amplifier or as in a switch. So when we are using a switch, we know that the switch can be either on or it can be in off condition. Okay. So first, the transistor switching. In transistor switching, we have got the two region of it working as cutoff region and another is an saturation region. So what happens in the cutoff region actually? In cutoff region, when we are getting the base a low input, okay, so when you are getting at a low input, your transistor would be in off condition, and when transistor is in off condition, your transistor will work as an open switch. So there would be no connectivity or no flow of the current through it. Okay, when you are discussing the saturation region, at that time you are getting the base a high input, and due to that, what is happening, the transistor is getting on and there is a connectivity of there, so your current can easily flow throughout it. So this is the basic concept regarding the transistor switching. Similarly, we have also get the diode switching. Now before we start the diode switching, let's get something clear, that is VCC would be equivalent to our high state, would be also equivalent to logic 1, and it would be also equivalent to the positive logic. Similarly, when you are saying at the ground, it would be low, it would be at zero logic, and it would be negative state. So basically, we have got diode here, a simple P and N junction here. Okay, so P type and N type material are used, and that is symbolized as anode here because of the positive, and cathode you are getting as negative. Okay, so diode also works under the switch on and switch off condition. So what happens when diode is in forward bias? Now, when what do you mean by forward bias? Forward bias means when you're connecting positive terminal with the positive terminal of the battery and negative with the negative terminal of the battery, at that time it is a forward bias, and if you do the reverse of it, that's why it is known as a reverse biased. Okay, so as we go with the forward bias, the anode is connected to the VCC, that is the plus, and it is connected to the cathode, to the ground, that is negative, with as we have explained above. Okay, so similarly in this case, what will be happening, your diode will be working as a closed switch, and closed switch means the circuit is getting completed. Okay, similarly when you are connecting with the diode as a switch off condition, we would be actually, it is diode would be in the reverse bias. Now what do you mean by reverse bias? At that time your anode, that is a positive side, is connected to the ground, that is the negative, and the negative is connected to the VCC, that is actually plus. So as you are reversed out the terminal, it will be working as an open switch. So these are the basic things that were required in the main circuit. So let us go with our main circuit. Main circuit of the basic DTL circuit is as shown below. Now this is the basic circuit. Now in the basic circuit, what is happening, we have got the, this is comparatively complex that we have studied regarding the RTL. Okay, but you will find it very familiar type. Why? Because some logics we have already prepared with that, and the logics are of the NAND gate. NAND gate, using the NAND gate logic, we are building up our DTL. So this DTL will be showing up you the logic of the NAND gate. Okay, and the NAND, you should remember that NAND is a combination of the AND plus NOT. So as we start over with this, VCC is there. Now VCC is distributed in the two part, given either to the R resistor and another to the RC. Now this follows up RC with the transistors collector, and output is also taken out from that only. Then you have got the transistor, this is your emitter, and at the this part is your base. Okay, now we go on the other side, there are the two diodes out there, this is DA and DB, and with that the inputs A and B terminals are also given to it, and this both the circuits are actually bridged out or connected with the help of the diode D1 and D2. Now you would be seeming familiar, this diagram looks like an AND gate, and this diagram looks like an NOT gate. Now simple thing is that AND gate, why? Because what is the logic of AND? In logic AND, both the inputs should be actually high. When it is high, the output you are getting high. Either of the input is zero, you would be getting nothing at the output. And in the inverter, we have got the output that whatever the input is given, the exact the reverse or the opposite of the output is there. As in digital, we have got only logic 1 and 0. So if 1 is provided, the output would be 0. And if output is input is 0, then the output would be 1. So now this is the observation table we have got. What we'll be doing, we will provide the input and then the diodes and then the transistor and then the output is there. So logically we will go step by step in our discussion and we'll discuss this entire summary of this logic table in the end of the theory. Okay, let's take the case. Now as we have got this logic two inputs. Okay, so the possible inputs would be four. Now, if this is the two input terminal DTL, okay. Now, if you want to get the more number of the terminal of the DTL, you are supposed to connect diodes here. This would be 3, 4, 5, 6. Like this, you can increase it. And this is nothing but the cascading the diodes in this manner. Okay. So as the two input is there, the possible inputs would be 4. So obviously there would be the 4 cases out there. So we will discuss first, that is the case 1. Now in case 1, this is the equivalent diagram that we have got of the DTL, and then we will be converting into the equivalent diagram. Now how we are doing it, let's go with the first input. Now as input is A is 0 and B is 0. Now you can also say that it is nothing but the connected to the ground. So when you are connecting this terminal A and terminal B to the ground, what is happening? See, VCC is provided to your diode DA, okay, as well as the diode DB, means positive is connected to the positive side of the diode. And when you are providing the 0 0, that means A and B is provided the logic ground, or you can also say negative. Hence this diode becomes the forward bias. So at that point of time, the diode, as it is becoming a forward bias, as we have discussed in previous way, that it would be working as a closed switch. So your diode, when we are writing DA is on and DB is on, it would be working as in short circuit, right? So now when it is working as in short circuit, entire current would be draining out from here. Okay. Now similarly, when you are providing this two diodes at that position of time, all the current is draining out here, so nothing would be coming out there. Okay. So as nothing is coming out there, the diode this would be in off condition. So when these two are in off condition, it would be equivalent as an open circuit. Okay. So as it becomes open circuit, you are giving nothing to the base of the transistor, and as nothing is given, that is nothing but equivalent to 0. And when it is 0, you know that the transistor will work as an open switch, and when it is working an open switch, it will be working as an off condition. So you can summarize it. This is the equivalent diagram provided here. In equivalent diagram, what is happening? The VCC is there. VC is provided to the two diode, that is diode DA and DB. It is short circuiting it, and because of that, all the current is draining out here. The diode D1 and D2 becomes open circuit, and hence your transistor also becomes open circuit. So now the VCC would be flowing out from here to here, and you are getting output as nothing but VCC, or you can say also it's logic high. Now this is a case number 1. Now we move to the case number 2. Now in case number 2, what you are doing, you are getting one terminal A as 0 and B as 1. So we will take out whatever the changes are there in your main circuit. So when you are getting it, VCC is there. So when you are getting A, now see, A is given 0. So this diode is getting ground, you can say that, and this is getting a VCC. Okay. So when you are getting this diode as a ground, so this will become short circuit. Okay. And when you are getting the VCC on the cathode side, you are getting a positive with minus. This will become reverse bias and it will behave as an open circuit. But still, your all the current is draining out here. So again, your diode D1 and D2 would be open circuit. Transistor would be also off condition, and the output would be you are getting out here. Okay. So we are summarizing it. So when it is input is 0 and dB equals to 1, at that time the diode DA will be in on condition, dB would be in off condition, and diode D1 and D2 would be also in off condition. Okay, and the transistor would be also in off condition. Hence you are getting the output VCC, or you can say as the logic 1. Okay, similarly in the case 3 also, but case 3 you are doing nothing but just inverting out the things, in manner. At this time the DA is getting the VCC and this is getting the ground. Okay, so what is happening now? Again the logic is same. The VC is there, Okay, so now DA is provided the VCC, so that will become open circuit. B would be becoming short circuit. Still, all the current is draining out from here. Okay, so again, your diode D1 and D2 would be open circuit, and because they are getting open circuited, nothing is given to your base of the transistor. Hence, this will become also an open circuit. So all the output you are receiving Y equals to VCC. So when you are getting that VCC, we are again just summarizing the things. As DA is giving 1, that is a logic 1, it will turn out to the reverse bias, and reverse bias it would be making it off. That is an off switch. But DB you are getting at a ground, so it would be in on condition, hence it would be draining out all the current throughout here. Okay. Now the because of this draining out, the D1 and D2, what would be the position? It would be in the off condition again. Now as these two are in off condition, nothing would be given to the base of the transistor, and nothing is given to the base of the transistor, so transistor would be also in the off condition. Hence, you would be getting all the Y at this point, you will be getting all the voltage out here that is equivalent to VCC. Now, how we are directly saying that we will be getting VCC? Because if we get here terminal here one, positive terminal, in another terminal here, that is a ground. So if we use the multimeter out there, so you would be getting all the VCC that is provided at this point, and the ground is getting as a ground terminal. Okay, this is how we are getting the logic. After that, the last part, now this is the most important and the significant part. Why? Because here you are getting both the input as one. Now we will know that if the both the inputs are one, means on the both of the diodes cathode you are actually providing VCC, and we know that if you are providing minus terminal of the diode a positive thing, it would be definitely in reverse bias. So when it is getting in the reverse bias, what would be happening? This DA and DB both would be in off condition, and when you are saying it off, it would be nothing but an open circuited. So when it is becoming now open circuited, what is happening? The VCC tends to flow here. Okay, but what is happening? Because of the open circuit, it is not able to flow, or it is not able to drain out. Okay, now it has got only one path available. That one path is nothing but this one. So when this you are getting this one path, so what is happening? The diode 1 and diode 2 are now only in this case would be getting in on state, and now when they are working as a closed switch, what is happening? Your transistor base is getting logic high. Now we know that if the transistor is getting logic high, what would be happening? It would be conducting, and it will be working as a closed switch. Now what is happening? VCC is traveling from here to here. Now, as per as this all logic, the transistor is short circuited, hence all the current drain out in this part. Hence, now if you use multimeter and drag it from here to this point, the across voltage that would be provided. Now, this one will show you in some other way. So when you are getting this voltage, okay, when you are getting in this voltage at that point of time, what is happening? You are getting across voltage very minimum, and minimum is nothing but output is zero. So diode D1 and D2 for the first time it gets on, transistor for the first time it gets on, and the output for the first time you are getting it zero. Okay, these are the logic of the four cases. So we can now conclude it. Now see, this is the summary wise. Okay, and we will conclude all the cases for it. So when we are getting for the all the cases for it, what is happening? This VCC is there. Okay, this diode input A and B is there. Okay, and now what we are doing, when you are getting 0 and 0, now 0 and 0 is provided, means this entire thing is draining out. At this time, what is happening? See, the DA and the DB, okay, this would be in your on condition. Now what I'm doing, on would be as dash and off would be across for me now. So when it is an on condition, we are getting at the dash condition, and the Q1 would be in off condition. Hence, you are getting the VCC as 1. Okay. Now the second case, when it is 0 and 1. Now either would be there. We know that as per as the discussion, it would be draining out. Okay. So draining out in this case, what would be happening? This would be again in on condition, and this would be in off condition. Hence, the transistor would be also in off condition, and you are getting the logic 1. Okay. Similarly, here also this would be in off condition, this would be in on condition, and in the last transistor would be also in the off condition, hence you are getting logic 1. Okay, again. Now the last case, in that the both would be in your off condition, and in that when it is getting in an off condition, what is happening? The transistor is first time getting in the conducting mode, that is should be in on condition, and the output received is your 0. So can see that the logic output 1, 1, 1 and 0 is there. So we can say that this is nothing but a NAND gate. Okay. So we can now prove that it is a basic DTL circuit using the NAND gate logic. Now the question is why we are using these two diodes out here in the middle of for the bridging out the thing. Now the requirement is, now if this two diode is not there, okay, and if the VCC is flowing out through this point, so transistor requires only the logic of approx zero point 0.6 volt to get it conducted. So that much voltage would be easily available at any point of time the transistor would be conducting. Okay. So that things not happen. That's why what is we are doing? We are doing that we are using this two diodes. So each would be having of the 0.6. The total 1.8 volt is required now. Now come on, in leakage you cannot have that 1.8 volt of the availability. So now when you actually measure across this, at that time you would be getting only 0.6, but when you across measure this it would be nothing but 1.8. So only when these two diode are in off condition, that is becoming the open circuit and this current is flowing through that condition, only your diode would be conducting and your transistor would be conducting, and then it would be flowing or draining out the current. Okay. So this was our basic DTL logic, and hence we have proved the logic of the NAND gate with the help of the DTL. Hope you guys understood this. See you next time.